Very casual. This is the third project from ME429, Propulsion System Preliminary Design. And we have a team here that will be talking about the system that goes with the previously presented liquid rocket engine. So with that, I'll turn it over to Isaac Anderson, who's the design team lead for this team.
Okay, good morning, everyone. Our team name is Alole, not Alole. We are the gimbaling system, as Aiden stated, for the liquid rocket engine, the ERAU, 1 metric ton rocket of thrust, 2,200 pounds. My name is Isaac Anderson. I'm the design team lead. This is Jan Kim. So first, we'd like to acknowledge people who have helped us on our way. Of course, our sponsor, which is Pyramid Space, as well as the faculty, Dr. Brenda Haven, Dr. Matthew Haslam, and the related team that we work with, which is Strava Designs, and a great team as well. Okay, so our presentation topics in terms of what we're going to talk about today, essentially, what is the purpose of our gimbaling system? Why do rockets need a gimbaling system? Do they need it because attitude control? Do they need it to look pretty? No, it definitely has to do with the attitude control. It has to do with trajectory change and systems like that as well. And we're going to talk about what is actually required, stated in our request for proposal, RFP, and how are we meeting those, and we'll discuss those as well as how we've imposed ourselves some goals that we feel that we can as well achieve. And we're going to talk about why don't we go with a conventional gimbal versus a translational gimbal, which ours is a translational gimbal, and we'll discuss exactly which each one is. And we'll compare between these two designs, why we went with our design, and what we're going to do in the future as well with our future work. So what is the purpose of a gimbaling system? And a gimbaling system is to provide a trajectory change, attitude control to a rocket, while it's either in outer space or getting to outer space, or throughout its entire flight envelope. We want to enable the attitude control. We want to be able to point the rocket into different attitudes, as well as be able to potentially land with some of the things that we were essentially receiving from our sponsor, is that they may have thought about doing that. As well as to change thrust relative to the center of gravity so that you can essentially do all these things matched together. If you see the diagram here on the right, this is your rocket engine. Laser pointer is not coming out too well. But this is your rocket engine here, and right up here at the top is your little gimbal. I have a better graphic in the next slide. And this is kind of how it fits right onto the rocket at the bottom as well. And this is actually a second stage rocket. Requirements that we received in our request for proposal. It has to be capable of providing at least a 6 degree of direction control. It has to be electrically linear actuated, and it has to have functionality that will go from 0 to 150,000 feet above ground. And also has to operate in the vacuum conditions. It has to be able to bear that 1 metric ton thrust, or 2,200 pounds. Also has to withstand the flight of 400 seconds, and has to be reusable, easily installed, and removable. All right, so what did we say we wanted to do? As our team, Alole, not Alole, we said we want to improve upon the design. We wanted to innovate, get something that's new, get something that maybe people haven't quite seen before, and see how we can progress that idea further on through our preliminary detail phase. We want to address potential drawbacks of using the conventional design, and that's why we moved over to our translational design. And we want to identify potential issues of our own design as well, and that's what we'll do in our comparison when we compare both of these to figure out which one we much prefer.
So moving on, I'll be talking about what we'll be doing to choose our gimbaling system. So the differences between a conventional gimbal, the existing gimbaling systems, and a translational gimbal. There are 3 main topics that we'll be talking about for each system. There's the structure itself, the mechanics, and how the actuators work. As a brief overview for conventional gimbal, the mechanics of a conventional gimbal are that they provide torque to the rocket by deflecting the actual rocket engine. Whereas for a translational gimbal, instead of deflecting the engine, it translates the center of thrust or the thrust vector away from the center axis of the rocket. The main structure of a conventional gimbal is a ball and socket or some variation of the ball and socket, whereas for our translational gimbal, it is a main frame with two load-bearing members. And finally, for the actuator systems, for a conventional gimbal, it's a minimum of two very powerful linear actuators. And for our final iteration of the translational gimbal, they're electric motor actuators. So moving on, we'll be talking about conventional gimbal mechanics. As stated earlier, conventional gimbals provide torque as a control mechanism to the rocket by deflecting the rocket engine nozzle and providing a torque via that deflection. So the actuators actually swivel the nozzle of the rocket to change the direction of the center of thrust relative to the center of gravity, and thus creating the moment arm for the torque. And moving on, that's the structure of a conventional gimbaling system. It's a ball and socket for the most part. There are variations on the ball and socket, but ball and socket is the most reliable that we've found. It's usually in very high thrust rockets, and because of the high thrust, there is a very high load that these ball and socket gimbaling systems have to bear. And because of that, they're made with very strong materials, and they're paired with powerful actuators. The actuators themselves for conventional gimbaling systems are usually hydraulic just because of the loading required on these actuators. And the size of these actuators is dependent on the power required and the attachment point chosen for a conventional gimbaling system. For a conventional gimbaling system, you can actually choose the attachment point that the actuators will attach to the engine nozzle. And you have a minimum of two, as stated earlier, but these actuators actually bear about a third of the thrust as the load, which actually varies with the angle of flight and the angle of deflection of the engine itself. But the trade-off is that it's a very simple control system as it provides direct angular displacement with these linear actuators. Moving on, some drawbacks of the conventional system. It's got a large vertical displacement when it's experiencing full thrust. We modeled a conventional gimbal with aluminum materials to reflect the materials we'll be using for a translational gimbal as well. We do realize that aluminum is not conventional material for a ball and socket gimbal design, but for the sake of actual comparison, we decided to go with an aluminum conventional gimbal design model. So for a large vertical deformation under compression, which means a full thrust condition, it had a maximum deformation of about 1/1500 of an inch. And this was with a diameter of about 4 inches for a conventional ball, which bears the brunt of the thrust. For tension, which means it's not actually experiencing thrust, and this is before takeoff, when it's bearing the weight of the engine as it's loading, it had a maximum displacement of about 700 of an inch. It's typically very heavy, a conventional gimbal system, based on the materials required. They're very heavy because of the load required as well. It's a large load on the actuators, as stated before, about a third of the actual loading. And it's expensive materials, and the thrust is always required for an attitude control. For conventional gimbal, you always need thrust to be able to actually change the attitude of the rocket. I'll be talking about the significance, or we'll be discussing the significance of this later when we're talking about our translation gimbal. And I'll hand it off to Isaac to talk about the concepts.
Okay. During our during the 4 phases within preliminary design, we've come up with a few concepts as well as ideas and improved upon them with iterations. As you can see here in phase 1 on the far left, the top one is the conventional gimbal, which is like a setting stone for us to say, okay, we're going to use that and compare it to whatever idea we can come up with that's going to be hopefully better. And that's why we're essentially the goal of our project. And so during phase 1, we came up with the conventional, and then we said, let's figure out a way that we can minimize some of the deformations, minimize some of these high load bearing actuators and weight as well. And think of something perhaps potentially more innovative. And so we came up with a translational gimbal. And the idea for the translational gimbal, then we progressed throughout the rest of our phases. Here's in the middle is phase 2 and 3 is our second translational gimbal. design. The reason why we switched over is due to structures and controls. And essentially, the main reason of the controls is the lateral space required of a translational gimbal is far greater than the lateral space required of a conventional gimbal, just because you have to translate. And so because of that, we came to a whole bunch of issues with, if you have a linear actuator with a shaft that conceals the rod that actuates, if you will, that it would have to extend the same distance of actuation, but on the other side, so that it would, essentially, if this was a 10-inch, if we needed to displace 10 inches, then we would have a 20-inch linear actuator system in order just to displace those 10 inches. And that was a huge demand in terms of asking a requirement of a rocket to be essentially 20 inches when we only want 10 inches of that to actually work. So we came with our final translational design in phase 4 and in phase 3. And essentially the way that this works is that we have actuators that actuate on a beam or an actuator track, and we'll once again dive into that in just a moment here. However, this way it only takes up about 12 inches with the housing and required equipment, as opposed to the 20 inches, which to us was a very good reduction. And this is just a diagram visualization of the gimbaling system that we have there. So translational gimbals. What is the mechanics? How do translational gimbals actually work? And so essentially what a translational gimbal does is that it displaces your center of thrust relative to your center of mass. So the way that you can think about it is that it's not a centerline thrust device. It is essentially providing a device to make it non-centerline thrust, to have the gimbaling actuation. And so essentially, in conventional gimbals, you want the centerline thrust to be straight through the center of mass, which is essentially what we're trying to capture, but use it instead for actuation. So the displacement of displacing our thrust line essentially causes a torque about the center of mass, which then causes it to change trajectory and attitude. This torque is then must be equal to the 6-degree torque of a conventional system, so that it is still comparable, as well as capable of fulfilling the RFP request for proposal requirements. Mass displacement can change location of the center of mass relative to the motion to alter the trajectory. Essentially, what this thing is capable of, we'll dive a little bit into more of some of the benefits, but regardless of the location and height of the center of mass, so long as that the mass so long as that the thrust stays within a constant amount, we can then gimbal the same amount without worrying about exactly the height location of the center of mass, which is a definite benefit here. So, some more about the structure of our translational gimbal. Frame with bearings to minimize friction, and we'll go into the track essentially more in the next few slides here. I don't know if you guys can see this little red laser pointer here, but this is the track here that the actuators actuate on. These are the beams that support the essentially the engine that hold it up, which then goes on top of the tracks. 2 load-bearing members are attached to the frame, and here are the load-bearing members. It supports the shaft that goes to the engine manifold, which is essentially this large T, which is then in compression when the thrust is operating. And the deformation of this system here is, and this is with material aluminum 775 T6. We did that for both the conventional and the translational for the comparison of the design of itself only. So in compression, we have about 4.5 thousandths of an inch, hundredth thousandths of an inch, yes. And in tension, this is where our design is not as capable as the conventional dive net a little bit in the next few slides here. However, in tension, it is about 1/10 of an inch deformation.
So the actuator system on our translational gimbal, the actuators are located on tracks and they move along gear tracks. The actuators rotate the gear, and the gear moves along these tracks, and that's how our actuator system actually moves our load-bearing members to also manipulate the shaft that actually supports the engine of the rocket. So the actuators are installed onto the load-bearing members, and there are 2 actuators per beam, and there are 2 beams on our machine. So we can actually use electric actuators with this because we've minimized the force and friction with our bearing system. The electrical actuators are not technically linear actuators because they don't have linear motion, they have gears on a track, but we can still use linear actuators, they're just not quite electric linear. Or we can still use electric actuators, they're just not linear. So moving on, that's our final preliminary design. Our final design after our iterations, we iterated due to the control systems, the lateral area, and our stress concentrations as discussed earlier by Sir Isaac over there. And this is our preliminary design as it has the smallest area, and our control systems fit within the area described just by the design. The ball bearings installed in the frame, as stated earlier, also reduce the friction to reduce the load on these actuators, bringing the total load on each actuator to a total of about 50 pounds per actuator for actuator spaces. We have the animation of how our system actually moves here. So the actuator is loaded onto both ends of the load-bearing members, move along those tracks, and the load-bearing members are located about the shaft in such a way that the shaft moves in the manner displayed. Moving on to the drawbacks of our translation.
Thank you. The drawbacks of our translational gimbal. Dimensions are dependent on the rocket, which means if your rocket is 10 inches or 8 inches, which is smaller than the 10 inches required for it, it wouldn't work essentially, because you have the gimbaling system would have to be protruding out the bottom. So larger lateral space required. The frame contains, like I said, to displace a 2,200 pound thrust on a similar rocket, it would have to displace 10 inches, and would have to overcome these inertial effects of the engine, whereas the conventional gimbal rotates it, and you can place where the actuators are attached to move through the center of mass of the engine. However, since we're at the top with our design, we would have to overcome moving the whole system from the top surface instead of at the center of mass, which applies a torque of moving it as well. Okay, and comparing the conventional translational systems, for the structural deformation of aluminum 7075 T6 under the same load, we have a conventional gimbal and structural deformation in compression of 0.153 of an inch deformation, and the translational is 4.5 thousandths of an inch. And for that, we can see that our comparison in terms of the structural in compression, the translational gimbal is far less than in terms of deformation. However, in tension or in the no thrust condition, the conventional gimbal only deforms 0.065 of an inch, and our translational system deforms a tenth of an inch, which is something that we're going to be working on to reduce moving forward with it. And the thrust required for attitude control. The conventional gimbal rotates and it displaces a vector of the thrust, and the translational does a displacement. But since it does the displacement, if you have no thrust, then let's say you're in outer space, you could displace to one direction, and that would change the actual rocket's attitude. So we have the capability with that. And factors for actuator size. The motor required for, power required for the motor is far less at the attachment points, and the power required for our motors are also a bit less.
So for actuator loading, as stated earlier, for a conventional gimbal, actuators have to bear about a third of the total thrust as a load, which also varies with our angle. And for the translational gimbal, the actuator loading, it only has to move about 50 pounds with friction. So in the comparison between the two, we found that the translational gimbal is, the actuators have to deal with a lot less stress and load. So we decided that the translational gimbal system in that sort of case is superior. And for the inertial effects, as also discussed earlier, for a conventional gimbal, they can be significantly reduced by moving the actuator attachment points closer to the center of mass of the engine. Whereas for a translational gimbal, these inertial effects cannot at all be affected or changed or reduced in any way, because the translational gimbal will always attach to a specific point on the engine, which would be the closest point of the engine manifold to the actual bulkhead. Moving on, how of our requirements from the request for proposal, which ones have been met by the conventional and translational systems? For a conventional system, we do get the 6-degree vector cone, as that is just a part of the design choice. You can't really use electric linear actuators with a conventional system just because of the loads required and tendency of electric linear actuators to fail under heavy loading. It would last a full service life with non-electric linear actuators, with hydraulic actuators, and it would last the full range of altitudes. It would bear the thrust. It would also last the 400 seconds, and it's easily installable and removable. Whereas for a translational gimbal, all of our requirements have been met. Though the full range of altitudes, we do have to comment the lubrication system for a bearing system. We do still have to look into just based on temperature ranges for the various altitudes. Moving on, this is what we'll be tackling in our detailed design, and I'll be handing off to Isaac to talk about structure.
Thank you very much. So in detailed design, our biggest concerns is figuring out ways that we can analyze, improve, and essentially test our design. And so the first thing that we're going to do is we're going to analyze the integrity of the components that are attached onto the components that we've already analyzed. So it would be something like the attachment point for the engine manifold to the bottom of our gimbaling system, and then the top of our gimbaling system to the bulkhead. We're also going to figure out a way to analyze how to minimize our maximum area that's required, as well as figure out exactly how much for our specific rocket, since in the RFP we weren't given dimensions or weights of the rocket. The temperatures for the gimbal and lubrication, as Jan stated before, we have to look into getting lubrication that's going to work in cryogenic temperatures, as well as, this is for our bearing system, at the top of our gimbaling. And we have to reevaluate our design, make sure that it's feasible. If the rocket is 8 inches and we need 10 inches, it's not going to work. So again, we have to allocate finances for testing and coordinate with Strava Designs so that we can have a group test and make sure that it all works for more physical testing. I'll switch it over to Jan to talk about detailed design for control.
So for our control system in detailed design, we still have to determine the response times of our actuators, as response times for a gimbaling system is one of the key components that you want to look at. So we have to look at our response times, the travel time of a linear actuator system versus the rotation of a gear along the track. We need to find out just how long it takes for the gimbal to actually reach the desired point for our required torque. We need to find the power required for our actuators, the exact power required as opposed to just 50 pounds. We need to calculate the cost of our actuators based on these power requirements, and we need to use the airball test on campus for a center of mass balancing to ensure that our control system works as desired. Here are our labor hours.
Okay, so we are now, with this last final presentation, we have gone to 8% above what our expected time was. I feel like our group, large group, put in a lot of effort and time into our project, and we will continue to do the same in detail. Are there any questions?
I know, so yes, certainly. We understand it's a very strange system, and we might not have tackled all of it.
So first of all, just preliminarily, I assume you're communicating heavily with the other team as far as understanding what your thrust profile is going to look like, and I guess as far as being able to do attitude maneuvers without thrust, it's just a matter of weight distribution.
That's correct.
Okay. That's actually that's cool. have these been done before? I've not heard of a translational gimbal.
The concept exists, but it hasn't been put into practice, mostly because the control system is required. Usually for a control system, just to be able to extend an actuator some certain amount on a conventional gimbal is significantly simpler than actually having to find exactly how many revolutions you need for a motor, and to be able to tackle all that, along with friction, along with all the stuff that varies with the flight profile. It's a bit of a nightmare.
Speaking of that, my main concern throughout all of this was predominantly looking at speed of getting to where you're going so that you can actually control, especially for landing, if that's your ultimate goal. That's obviously going to require a lot of fast movements.
So during our meeting with the sponsor, he seemed to indicate that landing wouldn't be too far off in terms of what he would like a system to do with the gimbal with this type of engine. However, this is not something that was stated in our RFP, so therefore it's not a direct requirement for our system.
Additionally, for the control system response time, that is something we'll be exploring more details.
Going back to slide 11, with your other alternative, so sticking with that was with the aluminum.
Yeah.
Okay, and that was the same loading as what you got on 14?
Yes, sir.
Okay.
200 pounds.
Okay. Obviously, just looking at that, I can see it's heavily deformed, and that is probably not even going to roll very well.
Yeah,
so as far as that, I guess I'm just kind of curious. Yes, it keeps it similar for material-wise, but functionally, it's not a very good comparison, considering you couldn't use that. So I guess as far as making a comparison between one versus the other, you'd obviously have to swap that component anyway to get a more accurate comparison.
Our comparison here for this evaluation is not looking at how the control system would react to a ball being like this, to the gimbal being like this, but instead how the structure itself would deform placed under the same load. So it is more of a structural test rather than a controls test of the system.
Okay. And then, as far as the inertials, we can go to, I guess it would be slide 15, and relevant. So for the inertial, you were talking about it slowing the system down. Can you possibly move the system to be in line with the center of mass? If you have it like, you said it was at the top of the, I guess it's at the top of the nozzle.
The engine.
Or it's attached to the top
of the engine.
Top of the engine. Can you move it down so that you basically move the tracks would be in line with the center of mass?
That would increase the area required beyond what we already have. And with a larger area, we risk not actually being attached to one.
Okay, that makes sense. Another primary concern, balls don't get stuck, but with a linear actuator, and it gets jammed with all the teeth and everything going on. Have you looked at that as a primary concern?
Yes, for our linear actuator, we actually have a redundancy system with at least 2 actuators for one direction. And that is to ensure that if we do have a controls failure with the actuator itself, that there will still be at least one capable of moving the system.
And then in similar line with the teeth, you said it was 50 pounds. I'm assuming the blunt of the force is onto the structure itself, and not the teeth. As far as the 50 pounds, I mean, obviously the teeth are going to be small anyway. Can they handle, the gears can handle that okay?
Yes, and designing the physical dimensions for the actuator system is something that we're going to work on in detail once we get that thrust profile, as well as figure out exactly the dimensions of the rocket.
Okay. And then as far as returning to the center line, so that you're not gimbaling, as far as a well-defined center line of where you want to return to for your baseline, do you have a plan for that?
I don't know that.
I mean, I guess
It would be part of our control system.
Okay.
We'll be looking into designing.
I'm not sure if you're going to be overshooting a lot. Is kind of where that was stemming from. Yeah, I think that's it.
picture below each of those would help you a lot, because
Okay.
you guys are too close. And for us, I knew what that was, because I kind of knew what you guys were up to. And I know conventional, and so some people in your audience will, some won't. So, you get to it later, but it helps them tag along with where you're going.
Right.
So that will help them sharpsmanship. Overall, the thing's very innovative, and I enjoy seeing what you're trying to do.
Great.
Is the frame handling the load? Are the two guys actuating handling, or is there like a cushion at the bulkhead that it's riding on in terms of, you see how I see on the far right when I see this large like piston looking thing up at the top. See how it looks like there's a piston on a bulkhead and then a connecting rod hanging down that you then actuate. Is the top of the piston actually handling the load?
During thrust, yes.
And there's ball bearings under there?
Yes,
Is that,
yes.
so I want to make sure I get what the gist is. Okay.
And those are the same ball bearings that would have to be lubricated with that cryogenic lubrication.
That's why I want to make sure I'm following you. You know what I mean? It's like I got to make sure I get it. Okay. Very nice.
Suppose we have time. Are there any more questions?
One suggestion, maybe title slides to separate your segments.
Oh.
I don't know if you got.
It's just with the amount that we actually have to switch off of just the two members, it's kind of like why include them? It would just
Does the Strava team have any concerns with their cryogenic feed lines while you guys are moving around?
Yeah, they most
Because
definitely
it's a different way than the conventional. So that's why, are you getting pushback?
We're currently working on ways to get around that. That is something that we're going to have to coordinate and definitely function very well in detail on. So, but we're definitely looking into it because that is another area that could be a setback, if you will, in the design.
I mean, there are other devices that do this similar kind of thing. There's obviously connections that work, and so you have to go scope what's been done and what else. It won't be rocket because that's not normal. But there's other things where this stuff happens. And weird cable tray tricks that work that way. So,
If you have time, effectiveness of when you have no thrust versus full thrust, to see how much effect you're actually going to have at no thrust and just having weight, is sort of an effectiveness of stuff.
on our actuators.
Yeah, just like to know how much attitude adjustments you can actually provide with the gimbaling system under a no thrust condition versus a full thrust condition.
I think the major reason for not performing those calculations yet is because we don't have the raw dimensions of the mass or the length or diameter.
you can come up with a novel length and stuff, just to run some numbers to help you get some feel, helps you add value to what you've been there already. Even if it's not the right numbers, you got some ballpark mental feel, which helps you and those kind of things. What's the benefit? And you may stumble into things you don't found.
That was definitely one of the goals of
I mean, it's a two-man team, so you can't expect you to do everything, but I mean, you can do some things where it's just nominal stuff just to run and to see what does this mean.
Or even the range of, not
Yeah.
nominal, but what are the extremes?
Yes.
And then how much does that affect, how efficient or effective are you at the different extremes that you would expect?
What do you think the upper limit is on thrust for this concept?
before.
Yeah, before some scaling thing goofs you up, okay? Or is there one? I mean, those are the kind of questions where, what's your niche?
Okay.
You know what I mean?
Yeah.
So in terms of thrust levels. Do the ball bearings embed into the bulkhead? If you get too high, you just can't get enough. I mean, those kind of weird things. I don't know the answer to that. It's fun to look at those kind of side things, so you know where your market is.
Definitely helps to sell it.
Yeah.
A non-technical question on slide 18. Why is overcome in a smaller font?
Why is it so? Well, yeah, I thought it was some keyword thing you guys were gonna foot stomp, and so I was waiting for the punchline.
Does it make it easier to overcome if it's a smaller
When we
overcomplicated that.
Yeah. It's so it's a smaller word, so it's easier to.
We honestly don't know what happened. Their formatting should be sad.
Yeah, because
Your eyes attracted to it, so we wait for a punchline and this come and you
as
guys
we
move on.
weren't really